Okay, so I welcome the viewers to this problem solving and live interaction session for the subject strength of materials that is offered by Professor K. Ramesh on the Swayam portal. So the idea is today we will be discussing the contents of week one, that is some problems. The idea behind this session is I'll be solving some problems, and as and when there are any questions, I'll try to address them. So you can stop me in between and ask the questions, or perhaps cumulatively take it up at the end. Over and above this, I suppose everyone knows that there is a forum in the Swayam portal. If you go to the Swayam portal, there'll be a Q&A tab. If we click on that, it'll take you to a Google Groups, which anybody can join, become a member, and then whatever questions you have, you can raise it there. There also, we'll try to address it. And if we are not able to address it there, we'll perhaps take it up in this session. Cumulatively, we'll overall address the questions there are. So I would urge everybody to join that forum. And also, this session, it will be conducted weekly once on Fridays, same timing, 6 to 8, uh, every week. And every week will be dedicated to that particular contents of the week. And it'll be the same link throughout the duration of this course, which is available on the. I suppose you would have found that link somewhere, which is how you've been able to join. So I encourage you to ask as many questions as there are. I'll try to address them. Even if I'm not able to address it right away, I'll at least make a note of it and try to address it in the subsequent sessions. So I hope you can bear with that. But and any constructive feedback there is on my delivery or the content or how whether my speed and explanation is clear or not is most welcome. I'll try to accommodate that also to the extent I can. So so with that, perhaps I'll get started. Before I start, are there any questions in general? If there are, please you're feel free to unmute and ask. Okay. All right. So also, you are welcome to ask anything on the chat box also. I'll try to address that. So, okay. With that, perhaps I'll get started then. And these weekly sessions, I'm presently recording them. So the recordings will also be made available to you in due course of time on the same Swayam portal page. And the notebook on which I'm writing here, that also I will post it in that same link so that you have it ready at your disposal. So, okay, with that, I hope my volume is all right. So I'll proceed to begin with the contents of week one. By the way, let me just introduce myself. My name is Ganesh Ramaswamy. I'm a PhD scholar in the Department of Applied Mechanics and Biomedical Engineering. I'm pursuing PhD under the guidance of Professor K. Ramesh and co-guidance of Professor U. Saravanan from the Civil Engineering Department. So once again, I welcome you all. So let us move on to the questions. But before we do, there is something that is important to address here. Given the sheer number of participants and courses there are in the Swayam portal, it is not possible to go for manual grading, which is why we have to go for computerized grading. And with that, there are certain constraints that are there. Because it is computerized grading, we cannot always ask multiple choice questions. So we would urge the participants or the students also to enter numbers. And those numbers have to be within a particular range for the computer to mark it as correct. So even though a student gets all the steps right, if there is some rounding error or something like that, it percolates towards the end. It accumulates towards the end, and perhaps the answer might go out of range and it might get marked as incorrect. Which is why it is important that everyone reads this instruction for the assignment carefully before answering. So basically, we will be going with 9.81 as our G value. And whenever there is a numerical type, you can just round it off to 2 digits and report. And for the various quantities that are asked, invariably it will be mentioned in the question what is the units that you are expected to report that in. However, I also urge you to be very comfortable with unit conversions, because in general, when as a practicing engineer, when we will come across different quantities, it will not be in the units that we always want. That can be simply multiplied. So invariably, we will require conversions. So it is very important that we become very conversant and comfortable with conversions. Also, there would be questions where even though the answer is compressive or negative, perhaps the answer is a compressive stress, or it is a vector component which is negative, we have to look out for the questions which ask for the magnitude. If the word magnitude is written over there, it is imperative that we have to report the absolute value in order for us to have that correctly. So I hope we can abide by these simple rules so that we don't lose out on that. And I just want to, although it, yes, please.
Sorry, my name is Jayakrishan.
Yeah, hi.
If I may ask,
Yes,
so you mentioned about the two decimal places rounding.
yes,
So so obviously when you have say multiplication or stuff like that,
yes,
you can have the rounding errors add up.
yes, yes.
So is this just related to? So would you advise that we deal with the whole set of decimals when we do multiplication, etc., and just round off the final answer, or
Yeah,
um,
actually, it will be preferable that you do that. But in any case, we
right?
have given enough leverage in the range in order to accommodate these deviations. But just in case, so that it doesn't accumulate out of range, I'm just mentioning it. So
Sure,
there is no
appreciate it.
need for apprehension that, whether we need to round it off at each step or towards the end. We have given a comfortable range. And we are also in a position to make corrections if need be, although we don't anticipate that need would arise. But for now, you can just proceed with rounding off at steps so that we are within the range. Anyway, I
All
don't
right,
think it
perfect.
should cause a problem, but I just wanted to get this out of the way so that it is conveyed properly to the
Sure,
participant.
appreciate it. Yeah,
All
thank you.
right, thank you. And many of you might be already conversant with it, but I just want to make a short remark on the units before we begin. So the units. So mainly, predominantly in this course, we will be dealing with stresses, strains, displacements, and so on. So for displacements, we already know what the unit is. It has the dimension of length, so it will be meter, millimeter, and so on. For strains, there are no units as such because it is a ratio. However, at times you will be seeing something like that. At times you will be seeing something like that, a microstrain, which basically indicates it is in the range of the order of 10 power minus 6. The ratio is already of the order of 10 power minus 6. Because of the paucity of space, we might confine it to writing it this way. So I hope there won't be any confusion. The major issue comes when we deal with stresses and elastic constants. So as we will see throughout this course, we'll have multiple elastic constants. And generally, for example, let me take the Young's modulus. So the Young's modulus, let me take for an example, let me take it to be of steel. So the steel's Young's modulus is around 200 GPa. The value is not important per se as of now. I'm just focusing on the units. So what does this GPa mean? I've noticed that some people have a problem in converting this towards the final answer. And even if they know the steps towards the end, some unit conversion, there is a problem and they try to lose out. Then they tend to lose out. I don't want that to happen, which is why I'm giving a basic brief about this. People might find it very pedestrian and basic, but I request you to bear with it so that everybody is on the same page. So this is nothing but 10 power 9 Pascal. Now what is 1 Pascal? Pascal is nothing but Newton per 1 Newton per meter square. This is the unit. So when we have when we have to substitute the value of Young's modulus in an equation, we have to ensure that it is substituted in the consistent units. Now, often we will come across a unit of stress. The SI unit will be MPa. Now, what is MPa? It is nothing but 10 power 6 Pascal, which is 10 power 6 Newton per meter square, which is also equal to 1 Newton per mm squared. So such conversions, I would urge anybody who is not comfortable with that to just practice around, so that whenever we substitute, because while solving questions, I will not be paying much attention to the exponents that I put in, but it is essential in order to account for the values correctly. So you can just take a note of this when we solve the questions. Okay, so with that out of the way, let us look at the first question. We'll build in from a little bit of theory towards some practical problems. So there is an assertion that a rigid body does not undergo deformation. The reason, in a rigid body, the distance between two constituent particles does not change when the body is subjected to external forces. Now we saw there is a course that we have done on engineering mechanics, which is the first level course, where when we take a body and when we have, let us say that we have two components, 2 points on that body, we subject it to some external force and moments. There are some external force and there are some couples applied, there are some supports and so on. So under the action of this, the distance between these 2 points does not change, which is why we don't worry about what is the internal response of this. We just see overall, does this body move, translate, rotate, and so on. That is what we saw in engineering mechanics. So that simplifies our problem, although it might not be realistic. For the first level analysis, it is very essential that we do that. So when the distance between 2 points in a body doesn't change, we in abstraction, we hypothesize that it is a rigid body. So the rigid body does not undergo deformation, and the reason is the distance between two constituent particles does not change when it is subjected to external forces. So if we were to remove the support here, it will be replaced by another force and a couple and so on. So under the action of these things, it does not change its shape or change its dimensions. So that is what the rigid body abstraction is all about. So these statements are true, and R is the actual reason for statement A, which is why it does not undergo deformation. And we are only interested in the external response. But in this course, as we will see, that will not be enough for us to solve some problems. We necessarily have to design such components. So for that, we need to know what is the internal response, in which case we will relax this assumption of the distance not being same. We will allow it to deform, albeit we will allow it to deform in a very small manner. The deformations will be very small. When the deformations are very small, we can apply all the forces to the initial system itself and go about our analysis. So that is the idea behind doing this. And also, just to mention aside, because I've also seen that some attendees have some language issue also. So just to say, I'm comfortable delivering it in English, and I also am conversant in Hindi and Tamil as well. So in case anybody wants me to explain something in Hindi or Tamil, they are most welcome to ask me, and I can accommodate that also. It should not be an issue as such. So I hope if anybody does have that issue, kindly let me know, and I'll try to explain that in Hindi or Tamil as well, to the extent I can. I hope that is okay.
So translate in Hindi also.
Translated, yeah. So whenever whenever I explain something, if you need me to explain it in Hindi, please prompt me so that I can do that. Because delivering the entire thing in Hindi and English might not be possible. But अगर मेरे को आपको कुछ समझाने की जरूरत है तो आप मेरे को बता दीजिए कि ये आप हिंदी में भी एक बार बता दीजिए तो मैं बता दूंगा. ठीक है आपको आपके लिए?
Okay,
हाँ.
sir.
Okay. So let us move on to the next question. Stress is defined as which of the following? Stress is a measure of deformation. It is a ratio between the deformation and the original length of deformation. a measure of the internal forces within a material that resist deformation, a measure of the velocity of deformation. So any guesses on which this is?
So I think option
C.
C.
Yes. Yeah, exactly. So when there is a body,
Sir, option B.
B. Okay, let us see why this is not the case. So basically we are having some member that is subjected to, let us say, a pull like this. So this is, okay, let me not go like that. Let me instead take it to be some force that is applied. So this member is subjected to some force. We are pulling it with some force. And if I cut like this, and I can actually see a cross-sectional area like this. It is a rectangular piece, let us say. This is a rectangular piece, and this has an area A. So at any point far away from the loading, at this point, what will be my stress? Stress will be nothing but F by A. This is what we have basically studied. 1 minute, my screen is not getting updated. Yeah. So this is what we have basically seen. We will see that stress has more deeper, explanations than just this F by A. But for the sake of this example, I limit it to F by A. So the stress is F by A. Whereas under the action of this force, what will happen to this member? It will actually first elongate and it will also contract laterally. So this will be kind of the final shape of that, where again the forces F is applied. So this is what it would have become. So when we see the area would have shrunk and this will become like this. So this will be the area after its deformation. We just take it that the difference between these two are not that big, so that we have to move from one coordinate system to the other. That is, we don't have to apply everything in the deformed coordinate system. We can still apply our all our equations in the first case, in this case where the force is just applied. This is what the assumption of small deformation means. So now if let us say this length was L, if this is L and this is some L plus some change in its length. So how do we define strain? Strain is denoted by epsilon. Strain is denoted by epsilon, which is change in length. So what is the final length? L plus delta L. What is the original length? L. So the change in length is L divided by the original length. So this is just one very basic explanation of strain. Of course, stresses and strain have more deeper meaning and more understanding that is needed. But for the sake of this example, I'm limiting it here. So it's not the measure of deformation. The ratio between the deformation and its original length is actually strain. Whereas when it is subjected to this, when it is subjected to a force like this, what will happen? Let us say that I take this here, I remove all this and I cut it, and I cut artificially. I just, for the sake of analysis, I cut the member like this. I forget about the rest of the part. So this is a cut section. So when I pull something like this, it just stays. It is not that it keeps on moving, which means some kind of equilibrium is set up. That equilibrium is set up because there is an internal stress that balances out the force that was applied. So this internal stress that balances out the force that was applied, this leads to equilibrium. So the material itself, when we are pulling, it is developing resistance inside in order to equilibrate the external forces that were applied, which is what this statement also says. A measure of the internal forces within the material that resists deformation. Why is it developing that? Why is it developing this stress? Because there is change in the distance between 2 points. The material doesn't want to allow it, so it is trying to resist it, which is what is the resistance that is getting built up. So is it clear, or I think I went through a circuitous way of explaining it, but I suppose I covered many peripheral aspects also. If it is unclear, yeah, okay.
Yes, sir.
If there are any questions, you please feel free to ask while I move on. Okay, so let us look at this question. So there is an assertion that there is no engineering without idealizations. Engineering involves dealing with complex real-world systems, and idealizations are essential for engineers to analyze and solve the problems efficiently. This is because even the simplest of problems, there are a lot of assumptions that go in. Because let us say a basic problem of a beam, let me take. We have all come across beams in our engineering mechanics. We saw a beam like this. We said that there is a hinged support like that, and then there is a roller like that. There is a simply supported beam, and then we applied a force like this, and we went about doing our analysis of calculating the reaction, shear force diagram, bending moment diagram. So for this, let us say that the reaction is applied exactly at the center. The force is, let us say, the applied exactly at the center. So what will this be? This will come out to be P by 2. This will come out to be P by 2. There will be a reaction here, which will also come out to be P by 2. Will there be any horizontal forces? There won't be. So we will see that the shear force diagram, we will just draw the shear force diagram and the bending moment diagram. And of course, this is incomplete without our sign convention. So the sign convention also I should mention. So we go about doing our analysis like this. But how many assumptions have we pushed under this is what we should be aware of. First of all, we have said there are no horizontal forces. In principle, there won't be. We said that there is a roller here. When there is a roller, if we were to zoom in here, we have a roller like this, or perhaps there are many rollers. We have just taken for granted that there is no friction that is getting developed there. So, which means if there is friction, there would be some horizontal resistance. But we have pushed that under the rug, saying that we have idealized the roller support as frictionless. We have idealized this pin that is over here. The pin that is over here that goes into the beam, we have idealized that to be frictionless. So there is no friction, we have said.
Sir, please drag that above colorful toolbar down.
Is it okay? All right. Yeah.
Yes, sir.
So yeah.
Thank you, sir.
And then now if we were to see at this point, if we were to zoom in, we have said that the beam is like that, and the force is exactly applied on at a point, at a molecule, which does not naturally happen. When we have such a high force that is getting applied, we always know that there will be some local deformation that will happen there. But even with all these assumptions inside, we simply go about calculating our reactions using our rigid body mechanics, and go about getting the shear force diagram and bending moment diagram. So these are certain idealizations that we have to make in order to approach this problem. If we are very rigid about accommodating every aspect of the problem into our mathematical analysis, then it will not be possible for us to get tangible answers. It will just be an endless research problem. Whereas we are engineers are in a need to deliver components, designs that are required for day-to-day activities, which is why which is why idealizations become very important. Yes, please. Someone had a question. Okay. So yes, both statements are true, and R is actually the reason. Yeah,
Option B, sir.
R is the reason for statement A. Okay. So let us look at this question. It says if the material properties are same at every point of the body under consideration, the material is which of the following is what is asked. So I also encourage whoever is watching, if you know the answer, you feel free to type it in the chat box. Yeah,
Isotropic.
isotropic. Very well. So I'll just give a brief about this, why this assumption is needed. So let us say that I'm just taking a simple example. Let us say we have a sheet of some material and we have to make designs based on the, we have to design some component which is to be cut out of this sheet. Now, if we have a sheet, if we don't make an assumption that it is homogeneous, then it would mean that if I cut out the portion from here, or instead if I cut it out from here, or maybe if I were to cut it out from here, so I have to do three different analysis. First, I have to cut the portion out of here, then I have to test that prototype and determine its material properties in this area, and then design, which is not a practical way to go about doing anything. Which is why we take it that given a material sheet, at each and every point, the elastic properties are same. So what I will do, I will cut one representative sample out of this material. I will test it. I will determine its properties and take it that it is uniform at every point in that sheet. Now it is a question that whether it is valid or not. In most cases with controlled manufacturing, it can be valid for a batch. Let us say the same material, I buy it from some different manufacturer with some different specifications. It is possible that it might have some different material properties. Then again, I will have to take one test piece out of their batch, test it, and ensure that I have got the material properties, and then I will go about assuming that it is same at every point in the material body under consideration. So this is the only practical assumption that I can actually go about I can go about designing my components. This is what is meant by homogeneous. Now let us see what is isotropic. Let us say that now I fix the location. I have told the workman that now that I have taken the assumption of homogeneity, it doesn't matter where I cut it, whether here I cut it or here I cut it or here. Let us say that the workman cuts it here. Now it is also possible that he can cut it like that. It is also possible that he can cut it in some other angle like that, maybe. So will the direction actually make a difference? It shouldn't make a difference because I don't have control over that. Now, when I actually have a material that is isotropic, what I mean to say is at in every direction at a point. Let us say that at this point, the red one, the red, I'm sorry, yeah, the red piece was cut by one worker, the mustard piece was cut by another worker. So these two should have the same material properties. So what does this mean? That at one point, given any direction, if my material properties don't vary with that direction, then it is called isotropic. So homogeneity is from point to point inside that material. And at one point, in every given direction, if the elastic property is same, it is called isotropic. Orthotropic, we will actually see that along two perpendicular directions, the properties will be different. For example, wood actually has grains that are aligned along the length. So when we pull it along its length, it has a lot of strength. Whereas if we pull it along its width, it will have less strength because the grains are not aligned in that direction. So it has two material properties along different directions. So when we are dealing with such materials, it becomes very important that we also convey how it is to be cut rather than just where. I hope it is clear. That is what it means to be orthotropic. Now, one step ahead, if we go, not only complementary angles, if it differs in every direction, then it is called anisotropic. So, for the first level course, we will actually confine our attention to only materials that are isotropic and homogeneous, so that we have one material. It doesn't matter where we cut it, at which location, and it doesn't matter in which direction we cut it. Whichever direction we cut or whichever location we cut, we have one material property, which will be Young's modulus, Poisson's ratio, and so on, which we will see as the course goes about. Our idea will be, so in our questions in this course, we will be getting the inputs that this material has so much elastic modulus, so much Poisson's ratio. By making our assumptions that we are dealing with only homogeneous and isotropic materials, we do not question where that is coming from. We will simply take it at face value that the material is homogeneous, so it doesn't matter where it was cut. This is what is the material property. Now I have to design for this material property. Is that clear? This is the idea behind the assumption of homogeneous and isotropic. I hope it is clear. If there are any questions, please feel free to ask. हाँ जी
सर मेरा क्वेश्चन है वो एक ही मटेरियल होमोजेनियस आइसोट्रोपिक हो सकता है क्या?
नहीं, वही हो सकता है का अजम्पशन है ना, ये तो हमारा आइडियलाइजेशन है. आप अगर आपका मटेरियल मैन्युफैक्चरिंग अगर कंट्रोल्ड है तो इट दिस assumption more or less stands. It is not a problem. अगर आप वुड ले रहे हैं, वुड में तो ग्रेन्स होते हैं, ऐसे लॉन्गिट्यूडनल ग्रेन्स होते हैं, तो उस वजह से उसमें आप assumption नहीं डाल सकते आइसोट्रोपिक का, क्योंकि दो डायरेक्शन में अलग अलग स्ट्रेंथ होता है. मगर आप अगर जैसे मेटल लेते हैं, मेटल शीट्स लेते हैं, तो इन मोस्ट केसेस अगर हमारा कंट्रोल्ड मैन्युफैक्चरिंग है तो हर पॉइंट पे मोर और लेस मटेरियल प्रॉपर्टी एक ही जैसा होगा और हर डायरेक्शन में एक ही जैसा होगा. तो इस वजह से हमें ज्यादा उस पर ध्यान देने की जरूरत नहीं है. अगर इसका कुछ स्पेशल रिक्वायरमेंट है कि इस डायरेक्शन में इसका स्ट्रेंथ ज्यादा होना चाहिए, तो हमें मटेरियल मैन्युफैक्चरिंग लेवल पे उसको एड्रेस करना पड़ेगा. ठीक है? ओके.
थैंक यू सर.
All right. So if the material properties are same at every point of the body under consideration, then the material is homogeneous. All right. So let us look at this question. Select the beam arrangements in which forces cannot be solved using the equations of statics alone. So what is being asked is which of these require. Okay, let us say that we come across such a problem. What is our first thing that we need to do? In order to design this beam, first of all, I need to know what the reactions are. That is, if I have a beam, I need to design this. I need to know at each and every point what is the stress or strain that is getting developed, and there will be some criteria that will be given to me, which I have to satisfy. For example, strength. Strength cannot exceed, strength is this much, so your stress in the body, beam cannot exceed this much. Then I will have one type of design. Stiffness criteria we will see. Deformation should be this much. So to control that, I have to design this beam. There are different criteria which we will see later. But my first and foremost, this thing is I have to analyze that at each and every point, what is the stress that is getting developed. For now, what do I know? In this beam, I know that there is a force that is getting applied. I also need the reaction here. When I isolate it as a free body, this is a fixed support. A fixed support will offer, it will just hold it, it will not allow it to move. So when we resolve it into components, it is resisting in the plane of the body, it is resisting movement along two directions, two mutually perpendicular directions. That is x and y. So some might ask, if this moves this way, is that not being resisted? Then why are we not drawing the reaction like that? That reaction actually can be split into two components, that is x and y, which is why we are taking two basic directions, x and y. All other directions can be resolved into components based on these two reactions. In addition to these two arrest of these two translations, this fixed support also offers a rotational constraint. That is, the beam, let us say that we have a pin support here. Let us say that we had a pin support here, it will try to rotate, but the fixed end doesn't let it rotate. So there will be a moment also getting developed. Now only when I know all these quantities can I go about and find out what is the stress that is acting at each and every point. So the very first step that I need to obtain the reactions, we were doing it comfortably by using equations of statics. What were the equations of statics? It was just the equilibrium equations. So in the plane of this paper, I say that for this beam, in the plane of this paper, I say that acceleration along this y direction is 0. Acceleration along this z direction is 0. And angular acceleration is 0. There is no rotation. Based on these three conditions, we arrived at three conditions: sigma fx equal to 0, sigma fy equal to 0, sigma m equal to 0. And we were applying these three equilibrium equations consistently, and we were finding out what were the reactions. So in this plane, we have three equations of equilibrium. So equations available is 3. Now from our basic mathematics, we know if we have three equations, maximum we can solve only for three unknowns. If we have three independent equations, we can only solve for three unknowns. So in this question, we just have to see which are the ones that that have more than three unknowns. So let us see that. In this question, how many are the unknowns? There is a vertical force, there is a vertical reaction, there is a horizontal reaction, and there is a moment that the fixed end will offer. So this has only three unknowns, and we have three equations of equilibrium. So this can be solved using statics. The question is asking which cannot be solved. So we just need to select which are the ones that cannot be solved. So the first one can be solved. Let us look at the second one. The second one also has two vertical reactions, two horizontal reactions, and two moments. So basically there are 6 unknowns and we have only 3 equations. So this cannot be solved using statics. This is one of our answers. Let us look at the next one. A hinge support offers a vertical reaction, a horizontal reaction, but it allows rotation. It does not constrain rotation. So there are only 2 unknowns. At the roller, we have only a vertical reaction. So there are only 3 unknowns and 3 equations. So this can be solved. So this is not part of our answer. Similarly, for the fourth one, we have vertical, horizontal. We have at the end, we have a vertical. Midway also, we have one roller support. So that will also offer a vertical reaction. So the unknowns are 4. Unknowns are 4. Equations are 3. So this also cannot be solved using statics. What is the fifth one? Fifth one is just the variant of the third one. We had this case. We have just taken this support. We have just taken this support and put it here. That is all we have done. So it has not changed anything as such. So it can still be solved using statics. So this is definitely not our answer. In the last case, if we see, we have a vertical reaction, a horizontal reaction, a moment at this end. At the other end, we have a vertical reaction. So how many are the unknowns? Unknowns equal to 4 and equations are 3. So this also forms part of our answer. Now there might be a question one might ask that I know that this beam, let us say the first case, this case, it is subjected to only vertical force. So there is no horizontal reaction that is getting developed. So horizontal reaction has to be 0. Then how do you say that it is an unknown? It is known that it is 0. Some might have that question. Why are we counting horizontal reaction as unknown when we can clearly see that it is 0? We actually, what we have done is we have already used one of this equation, sigma f x, sigma f horizontal equal to 0, in order to conclude that that reaction is 0. Implicitly, we have not explicitly done it, but in our mind, we know that there is no horizontal force. It is not moving horizontally, so there is no acceleration. That is why the horizontal force is 0. Unknowingly, we might have done it, but we might still be thinking, why is it an unknown? So when we actually cancel out the horizontal force to be 0, we have already utilized one of these reactions, one of these equations that are available. That is sigma horizontal equal to 0, which is why it still counts. I hope it makes sense and I've conveyed the point clearly. If there are any questions, please feel free to ask. And if anybody wants me to explain this in Hindi also, I can do. Please feel free to ask. I hope this is clear. All right. So why are we actually doing this exercise? Why are we trying to find out which are the beams that cannot be solved using statics alone? Because whichever could be solved using statics alone, we have already solved them in our engineering mechanics course. We have found out the reactions, we have drawn the free body diagrams, we have drawn the shear force diagram, bending moment diagram, or axial force diagram, as the case may be. Now there are problems which we can clearly see where I cannot solve it using statics. I need something more. What is that something more? That something more will come from the deformation of the component. For example, let me take the last case. Let me take the last beam. So the beam is like this. It is fixed at this end. And I have some load that is applied. So if the problem was just this, for example, was a cantilever, let us say. So if the beam was like this, a cantilever, then it was very easy for me to solve using statics. Now what we have done, because this was deforming too much, we have put a support here. We have put a roller support here in order to limit that deformation. Now this has suddenly become statically indeterminate. So in order for me to calculate this reaction, how much this reaction will be, I cannot solve it just using statics alone. So I have to bring in the deformation. How do I bring that in? Let us just see briefly how do we bring that in. This will actually offer this kind of a reaction. So what we will do, we will first remove this support. We will first remove this support and let it deform. It will deform something like this, let us say. This will go to this point. Then we will take this beam again. I'll remove the load this time. I'll just put the support as an external reaction. So what I have is the sum of the bottom two add up to the final result. For the first one, I know I can solve it by statics alone. For the second one, I need to bring in the deformation picture. Because of these two reactions, because of these two forces that are getting applied, it will add up to my original problem. So this is where we also bring in the deformation picture in order to solve the problem, in order to find out the unknowns. Is it clear? Are there any questions?
Can you please repeat it?
Okay, so basically, let us say that we have a cantilever. We have a cantilever. We were able to solve this. Now, what we have done, we have propped it at one end. We have put one support. Now, suddenly, this is no longer what do you say? This is no longer compatible to be solved by equations of statics alone. We also need to bring in the deformation because we need one more additional equations because there are four unknowns. So there are basically four unknowns now, but there are only three equations at our disposal. So the fourth equation will come out of the deformation, which we will study in this course. This is the inspiration behind this question, why we need to identify whether the problem can be solved by statics alone. If we see it can be solved by statics alone, we don't even need to delve into this course. But there are beams, there are members that actually have more supports than are necessary for basic equilibrium. In order to solve such problems, we need to understand the deformation of the objects so that we can actually calculate the unknown reactions and subsequently design the components. Is it clear? This is what I was saying.
Yes, sir.
Okay, okay. All right. So let us look at this question. I'll just move the thing here. So if we don't understand these colors, let us not be worried. We have a dedicated week for that. But just the broad strokes I will give. This method is basically called photoelasticity. So what this method does in this experimental method, we have some materials. When we pull it and place it in one arrangement called a polariscope, that is, it will have some components and it will have a light source. When we place the component there and pull it, it actually shows us how the stresses develop in that material, which is very interesting to see. We are physically able to see because when humans get stressed, they exhibit some symptoms. Similarly, we can even see how a material is getting stressed real time. When we actually pull the component, it will show some patterns which are representative of how the stresses are evolving in that material. So that is the experimental technique of photoelasticity. Now what this question is saying is there is a long bar. There is a long bar, long axial specific tension strip, which we are trying to pull at both the ends. In general, if we have a strip like this, and then we try to pull it, when we go away from the loading points, we will see that voice is not audible. Is my voice audible, sir? Yes, please. Sahana.
Yes, sir.
Yeah. Sahana, yeah, go ahead, please. Sahana Gobur, please ask what is it? I think others are able to hear me. So I think Sahana, why don't you just maybe there is some issue with your audio. You can just leave the meeting and join back again so that yeah, stop. Okay. So what do we anticipate that there is a material strip, let us say, and we are trying to pull it away from the loading points. We will actually see that the stresses are more or less uniform. But by the introduction of just a small hole here, the picture totally changes. That is what we are that is what we are seeing here. When we load this, it should have been a uniform color. Whereas when we have the hole like that, we see that there are more colors, more patterns that are getting formed. We will see how to interpret these patterns. That will come in a later class. But basically what we are seeing is we are physically seeing the effect of a hole on a tension strip. So one might argue that we have a tension strip and just we have a small hole. What is that going to do anyway? But we are seeing that it makes a marked difference in our stress field. So if we simply ignore that hole and take the stresses to be uniform and design our components, and let us say that due to manufacturing there is a hole that is left in that component, we see that our design is no longer valid. So it is very important to understand the effects of inclusions and defects like this. But this will delve more into a field called fracture mechanics. Presently, we only take our tension strip to be free of any defects, but it is also important we understand the limitations of what we are studying. We should not think that once we have done this course, we know all the design in the world, because there are certain assumptions that have gone in here which might get violated in some cases where some special attention would be required. That is the inspiration behind this question. Okay, so a tension strip with a hole is shown in the figure. Choose the correct answers. More fringes near hole indicate stress concentration zones. So what basically happens is, when we have a section like this, let us say I take a section, or let me just copy this. Is my speed of delivery okay, or am I going too fast or slow? Could I get some feedback on that? If I'm going too fast, I can slow down also, because
It's okay, sir.
it's okay, fine, all right. Thank you. Okay, thank you, thank you. So let us say that I take this specimen, I make a cut here, I throw away the rest, I just retain I just want to see what is happening here. Now, as we saw, this component, I have cut it here. So this is not moving. I have pulled it and it is stopping somewhere. So it is in equilibrium, which means there will be stresses developed like this. So this is my force P that was applied, and this will be some sigma. Now let us say this tension specimen has an area of A. So P will be equal to sigma by A. I can see that my stress is uniform throughout the depth. I can see that it is uniform. This is uniform width. Whereas if I were to take the same thing, this time instead of cutting it here, I'll cut it at the hole. Now what will remain of this? This will be the cut section. This will be the cut section. I'll have the hole like that. So the stresses will no longer be uniform here. What happens is stresses will go like that and it will build up. Here there is no material. So I'm just qualitatively trying to explain what is happening. So the stresses are no longer uniform. The stresses are a function of the depth. The stresses show a variation like that. It is no longer straight. So if we were to design our components based on this stress, we can see that at the hole it is getting exceeded by some factor, which we will see it is called stress concentration factor. It will come later. But what I'm trying to say is, if there is a small hole, the stresses shoot up near the hole, and that is actually showing. We can actually see that based on these stresses, based on these patterns, which is getting accumulated towards the hole. So more fringes near the hole indicates stress concentration. Yes, sorry. Yes, more fringes near the hole is just an artifact, and the hole does not alter the stresses much. We have discussed that photoelasticity is the technique which actually shows the stresses in real time when we actually apply the forces. So it is not some artifact. It is coming from the mechanics of the problem. And it actually indicates that the stress is getting concentrated over there. When no hole is present in the specimen for a given load, a uniform color appears in the region away from the loading point. This we can just see from here. We have the hole here. If we were to see this section, and in fact, I will just take this section out separately so that we are able to appreciate it better. I'll just paste it here. Let me crop it like that. I'm sorry, 1 minute. Here I will see that the color is more or less constant, is it not? If we compare it to this place, if I take a section here, let us say, for example, now at the hole, I'm able to see so many color changes. But away from the hole, I'm able to see that the color is more or less uniform. I'm taking just that strip because when we see the entire picture, it generally clouds our judgment. That is why I'm just taking a small strip. So we are able to see that as we move away from the load, as we move away from the hole, the color is more or less getting uniform. Again, when we go very near the point of force application, there also we will see some stress concentration. So when the no hole is present in the specimen, it will have more or less uniform color at regions far away from the loading ends. This is quite true. We are also qualitatively able to see it. Internal resistance is uniform at section A due to applied load P. We just saw that when we cut a section like this, it has to balance out the force P. The stresses get developed like this. It is not uniform. It has a variation. It shoots up near the hole and then it becomes more or less constant near the ends. So this is not true. Internal stress is not so at section A, whereas at section B, it is more or less uniform of a single color. So this is true. Is it clear? Any questions?
Yes,
Yeah.
sir. I have a
Yes, please
question.
go ahead.
What is the region represents of photoelastic during applied tension?
What it represents?
क्वेश्चन ये है कि मेरा
हाँ
क्वेश्चन ये है कि जब हम किसी मटेरियल पे अगर
जी
हम फोर्स अप्लाई
जी
करते हैं तो फोटो इलास्टिक पैटर्न क्यों रिप्रेजेंट करता
हाँ
है
मैं
वो?
अभी आपको बताता हूँ अच्छा क्वेश्चन है तो देखिए अभी हम इसमें स्ट्रेंथ ऑफ मटेरियल्स में हम स्ट्रेसेस को देखेंगे देयर इज समथिंग कॉल्ड प्रिंसिपल स्ट्रेसेस जैसे मान लीजिए एक प्लेन है हम जैसे भी लोड लगाएं एक पॉइंट पे दो प्रिंसिपल स्ट्रेस डेवलप होंगे एक मैक्सिमम होगा एक मिनिमम होगा किसी भी लोड के लिए तो फोटो इलास्टिसिटी जो हमको ये पैटर्न देता है जो भी हम देख रहे हैं ये जो कलर देख रहे हैं जैसे ये पूरा नीला कलर है ना ये जो हम देख रहे हैं तो ये पूरा नीला कलर क्या रिप्रेजेंट कर रहा है ये कोई सिग्मा ये जो प्रिंसिपल स्ट्रेस है इसको हम सिग्मा 1 सिग्मा 2 से डिनोट करते हैं ये क्या होता है इसके बारे में हम जानेंगे अभी कमिंग वीक्स में कि सिग्मा 1 कैसे कैलकुलेट होता है सिग्मा 2 कैसे कैलकुलेट होता है किसी भी पॉइंट पे पर जैसे ये जो फोटोइलास्टिक फ्रिंज पैटर्न है जैसे ये जो नीला कलर है अगर हम उन सारे पॉइंट को ज्वाइन करें जहां पे एक ही जैसा नीला कलर है तो ये वाला ऐसा कर्व बनते दिखेगा ये कर्व क्या रिप्रेजेंट करता है सिग्मा 1 माइनस सिग्मा 2 इक्वल टू सम कांस्टेंट तो फोटोइलास्टिसिटी जो हमको पैटर्न देता है वो बेसिकली प्रिंसिपल स्ट्रेस के डिफरेंस का पैटर्न देता है जैसे और ऐसे आप इसको और भी लोड करेंगे तो एक और पैटर्न बनता दिखेगा और किसी रंग का जब उन सारे पॉइंट को हम ज्वाइन करेंगे तो वो सिग्मा 1 माइनस सिग्मा 2 इक्वल टू कोई और कांस्टेंट देगा सिग्मा 1 माइनस सिग्मा 2 इक्वल टू 1 एमपीए दूसरा होगा सिग्मा 1 माइनस सिग्मा 2 इक्वल टू 2 एमपीए ऐसे बढ़ता जाएगा तो फोटो इलास्टिसिटी जो हमको पैटर्न देता है वो मैकेनिक्स पॉइंट ऑफ व्यू से क्या होता है वो होता है सिग्मा 1 माइनस सिग्मा 2 और सिग्मा 1 और सिग्मा 2 क्या होते हैं तो इन्हें कहते हैं प्रिंसिपल स्ट्रेसेस जो हम अभी आगे आपको मेरे को पता नहीं है कि आपको अभी इसके बारे में जानकारी है कि नहीं अगर नहीं है तो कोई घबराने की बात नहीं है अभी हम आगे चल के देखेंगे उसे कि वो सिग्मा 1 सिग्मा 2 क्या होता है और इनफैक्ट किसी भी प्रॉब्लम के लिए हम खुद ही देखेंगे कि फोटोइलास्टिक पैटर्न कैसे प्लॉट कर सकते हैं है ना सो हैव आई Yeah,
यस
okay.
सर
I hope I've answered. Yeah,
सर
yeah, please go ahead. हाँ
सर
जी,
सर मेरा एक और
जी,
क्वेश्चन है, जो नीला कर जो रिप्रेजेंट
हाँ,
कर रहा है, तो हम ये भी कह सकते हैं कि वहां पे जो शेयर स्ट्रेस ज्यादा
हाँ,
होगा, और जो आसपास के जो कलर दिखा रहा है वहां पे शेयर स्ट्रेस कम
हाँ,
होगा, ये भी डिफाइन कर
हाँ,
सकते हैं।
डिफाइन कर सकते हैं, बिल्कुल। तो आप ये कह रहे हैं कि जैसे मान लेते हैं, मैं यही क्यों कह रहा हूँ कि इस जगह पे मान लेते हैं कि स्ट्रेस का कुछ वैल्यू है 5, हम ले लेते हैं एग्जाम के लिए। तो जैसे-जैसे हम यहाँ पे जाते हैं, यहाँ पे एक और पैटर्न बनता दिख रहा है, उसका वैल्यू 4 भी हो सकता है या फिर 6 भी हो सकता है। तो आप कह रहे हैं कि ये ज़रूरी थोड़ी है कि इस डायरेक्शन का 6 ही हो, 4 क्यों ना हो? ये आप यही पूछ रहे हैं?
यस सर।
हाँ, तो इसके लिए हमको मैकेनिक्स पॉइंट ऑफ व्यू से भी देखना पड़ेगा कि कौन से मतलब एक ना इसका एक डायरेक्शन होता है, डायरेक्शन ऑफ इंक्रीज ऑफ ग्रेडियंट, where the stresses is increasing. It can be reversal of gradient also, but for जैसे ये प्लेट विद होल का जो प्रॉब्लम है, इसका मैकेनिकली हमारे पास सॉल्यूशन है, भले इस कोर्स में नहीं है, अगले कोर्स में है, मगर हमको पता है कि सबसे ज्यादा स्ट्रेस इस प्रॉब्लम का यहाँ पे बनता है, यहाँ पे बनता है। तो इस वजह से हमें ये फ्रिंज ऑर्डर का नंबरिंग हम इजीली कर सकते हैं कि कौन सा हाउ इट इंक्रीजेस फॉर एन अननोन प्रॉब्लम। जैसे आप बता रहे हैं कि आप ठीक बोल रहे हैं, इट विल रिक्वायर सम मोर एफर्ट in order for us to understand in which direction stress is increasing. Is it clear? Okay,
यस सर।
okay. Yes, sir. Somebody had Dr. Anbumalar. Oh, has he left the meeting? Yeah.
s-
Yes, please. Yeah,
excuse
go.
me if I
Yes,
may
please.
ask. Um, so what does sigma 1 minus sigma 2
It
represent?
represents
So sigma 1 I understand.
uh,
So as a physical quantity, what does it represent?
it represents the difference of principal stresses equal to some constant. Now, in let us say that we have a are you aware of the concept of principal stresses? It will be
Yeah,
okay,
yes, I
okay.
am.
In
Yeah.
that case, if for others who are not aware of this, there is no need to worry. We will be covering it in great detail as the course goes about. But just to answer Mr. Jayakrishnan's question, basically, if we were to have just this applied, just this force applied, at any point that is sufficiently away from the loading point, we know that our sigma 1 is just P by A. Sigma 2 is 0 in the plane. In the plane of the
Mhm.
problem, we have only two principal stresses, out of which one is P by A, one is 0. So sigma 1 minus sigma 2 comes out to be just P by A, which happens to be a constant. And that constant is
Right.
getting represented in the color. It is just a constant color. So every color, every RGB of that color is characteristic of one number, which represents sigma 1 minus sigma 2. Depending on how this difference varies, our color also will vary.
Right.
Yeah.
Okay. Yeah, maybe this will get covered
It will, it will. Yes.
I'm still not clear on
No,
what it physically
no,
means,
no.
but maybe we can discuss it. Yeah.
I welcome you to please ask the question so that I can try to convincingly answer you.
Yeah. No, I was just trying to
Okay.
understand. So I understand sigma 1 is the max
Yes.
principle, sigma 2 is the min
Yeah.
principle. And here for a uniaxial stress state, you know, it is equal to
Yeah.
P by A. But just wondering I also know that it's the diameter of the Mohr circle,
Yeah.
etc. But just from a general
Yeah.
perspective, I mean, physically, for example, sigma 1 is the plane along which you have the
Stress.
maximum
Yes.
stress,
Yeah.
etc. So what does sigma 1 minus sigma 2 represent? That's what I was trying to understand.
Okay. Uh, all right. Let me address it from another way. Let us say that this is constant, and we know sigma 1 is along the x direction. So this physically implies that if I were to cut it here, the plane of failure, when I have a maximum principal stress that is getting applied, the plane of failure will be vertical if it is
Uh-huh.
a brittle material. If it is a ductile material, we know it fails by shear, so it will move in some other direction. So it also gives us another way to gauge in which direction, because principal stress directions are very important. at a given point, there might be infinitely many directions that are that the plane can take. But our interest is to find out in which direction the maximum principal stresses occur, so that we are able to make some predictions about its failure when it is subjected to extreme loading conditions. This gives us a via media in order to understand that also. I'm not sure if
Okay.
I've convincingly given you the answer. If you're not convinced, I welcome you to ask some probing questions so that I can try to address it.
Sure.
Yeah. Yeah.
Yeah, I'll have a
All
think,
right.
and
Right.
maybe in
Yeah.
the later
Sure. Sure.
classes I can. Yeah.
Yeah.
Thank you.
All right. Okay. So that is what is the brief about photoelasticity, and this is important to give this brief because our professor K. Ramesh, he is an expert in this photoelasticity field. And in fact, throughout the course, many of the examples we have tried to cover it using experiments. We have shown you the experimental results in order to show it convincingly that this is how it is in physical reality. And most of those results will be from photoelasticity, which is why it becomes important. And there is absolutely no need for apprehension or worry that you don't understand it presently, because we have a dedicated lecture on photoelasticity also. This was just to enthuse the learners that there is something like this, which where we are able to see the colors as and when we apply the forces, we are able to see the colors. So it is just some enthusiasm. We will go about seeing this quantitatively as we proceed in the course. So you please bear with it, and I encourage you to ask as many questions as there are, as you have.
Sorry.
Yes,
Can
please.
I ask
Yeah,
you
go
one more
ahead.
question?
No, no
So
problem.
sorry.
Go ahead.
Um, uh, the fringe pattern that you've shown here, I assume, is for a ductile material, right?
This is basically for
Would
epoxy.
it?
Yeah,
Okay.
it's a linear elastic material, and it is well below the. It we are dealing only in the elastic range presently.
Right. I
Yeah,
was just wondering if brittle material would also show a
this
similar.
is brittle actually.
Uh,
Yeah,
this is
yeah.
brittle, right?
And in fact, even ductile materials, in the linear range, when we see as the scope of the course goes, as far as the scope of the course goes, in the linear elastic range, it won't be any different. Yeah.
Okay.
And in fact, when we even deal with plane stress, as we will see later, what we will find surprising is if we take an aluminum disc and if we take an epoxy disc, a polymer disc, if we were to press it, what we will conjecture, what we will think is that stresses would be more in aluminum and less in epoxy, whereas stresses always remain the same. It is independent of the material. When we are dealing with a sheet for plane stress, stresses remain the same, but strains don't remain the same. We will see that in detail.
Right.
Yeah. All right.
Sure.
Okay.
Sure. Thank you.
Okay. So let us look at this question. Two cylindrical rods AB and BC are welded together. So we have two rods. Let me just draw the outline of those two rods. We have two rods like this. And then we have 40 kilonewton and 30 kilonewton applied. Okay. So we have, and the weld is over here. I hope that you can appreciate. Weld is over there. So these two cylindrical rods are welded together and loaded as shown in the figure. If the average stress must not exceed 140 MPa in either rods, then answer the following question. So what we need to do is, this question says that we have to design uh, such an assembly so that the stress does not vary, stress does not exceed 140 MPa anywhere, the average stress. Presently, our understanding of stress is P by A. Whatever is my screen is not getting updated, or I don't know what is the issue. 1 minute. Yeah, okay, it is getting updated. All right, so presently we know only this much. We know stress is load by area, and then strain, as we discussed, is nothing but change in length by original length. That is sigma epsilon is delta L by L. Okay. Now we have, in fact, let me take it up in a new. Presently, we know that stress is load by area, which is represented like this. We know strain is change in length by original, which is represented like this. And then we have studied in our high school, basically Hooke's law. Which says that stress is proportional to strain is what it says. And that proportionality constant is nothing but our Young's modulus. This is very basic information that we have presently. Granted, it is not sufficient to solve all the problems, but this is as far as we know presently. We will see how it will get modified and how many components will start coming into this. But for the sake of this simple problem, let us just keep in mind these aspects. Now, if I were to substitute into this, let me substitute into this problem. Sigma is P by A. So P by A is equal to E into epsilon is delta L by L. L by L. So from here, delta L comes out to be PL by A E. This is another useful relation that we have. What does this relation tell us? That if there is a member that is subjected to axial pull with a force P, and if it has a length L, if it has a cross-sectional area E, and if it is made of a material that has Young's modulus E, then the change in length will be this much. That is all it says. I hope this is clear to everybody. Basic relations. If there are any questions, please ask. Yeah.
Yes, sir.
It's clear. Okay, thank you. So what I have done, how we have defined stress is just load by area. How we have defined strain, change in length by original length. How we have related these two by something called Hooke's law. The very basic version of Hooke's law we have studied in our school. Sigma is E by epsilon. Or we would have studied the load is directly proportional to displacement in a spring, for example. It is the similar, it is the analog of that in mechanics. And I have just substituted and I have got these three expressions. So we just need to keep these three expressions in mind presently, and let us operate with that and see how many problems we can solve. As and when we encounter a bigger issue, we will try to define more things and go about solving it. So with this preamble, let us try to attempt this question. It says that this assembly has to be designed. It is loaded in this and this way. If the average stress must not exceed 140 MPa, answer the following question. So let me take this assembly apart. I have taken it apart. What I will do, I will separate it out like that. And let us take that this force is applied here. So I have not done anything. I have just separated out the components. Basically, I am trying to draw the free body diagram of that. And this is a better way to proceed when we go about. So let us take the bar AB. This is AB. Now we have applied it with 40 kilonewton. On the top, it is actually fixed. So when we separate it out, as we did in beams, we have to compensate that by a force, by a reaction force. So let me draw that reaction force, reaction at A. So far, so good. Actually speaking, in the free body diagram, my weight should also come. Mg should be acting. But The question says I can neglect the self weight of the rods, which is very less as compared to the loads applied. Hence, I can safely remove this from my free body diagram. But nonetheless, we should remember only when the statement is given, we should exclude it. Is the free body diagram of AB complete? Sir, does moment also act as the fixed end? It's a good question. Presently, in this context, we are dealing with axial rods. It says rods. So predominantly there is only pull. If I were to apply a force like this, then I will also have bending that will come about. But since we are only looking at axial pull presently for the sake of this problem, I have not brought in the bending moment. Otherwise it will come. Rods are predominantly axial members. Beams will take bending. So we will discuss all these separately. Towards the end, we will collate them and do a comprehensive problem at a later stage. Is it clear, Mr. Ajit? Okay, all right. So is the free body diagram complete presently? We have actually compensated for the weight because it says it doesn't have any self weight. So we have avoided that. The 40 kilonewton that was applied, I have applied that. The reaction at A, I have removed the support and I replaced it by a reaction. But there is also one more component that is welded together with this. I have not accounted for the interaction of that component. Let us say that it provides a pull. It provides another pull. Let me put it in some other color. This is F on A due to F on A due to, or let me call it 1 and 2. Let me call this 1. Let me call this 2. This is basically F on 1 due to 2. There will be a connection, so it will apply some force. So now the free body diagram is complete. Now when I go to the other free body diagram, again this will have some mg, but since it is given to be ignored, the mass is to be ignored, I will not put that. Is there anything else that is getting applied? The Newton's third law pair of this force has to be applied in that also. So what I'll do, I'll just make a copy of this. Now there might be a question whether to apply it like this or like this. So this is where we have to be careful. Once that we have decided on one body, the force is like this, its Newton's third law pair has to be applied in the opposite direction in the other body. This is something to be kept in mind throughout the course. So because we have decided F12 is pointing downward, this will be F21. And from Newton's third law, we know F12 is nothing but negative F21. So both the forces are same. So I may well drop the subscripts now. So what I'll do after this is what it is. So after applying Newton's third law, I have dropped the subscripts. I have just written F. Okay. So now the free body diagrams are complete in all respects. Are there any questions now? Although this question can be solved very simply, I'm going into details of the free body diagram because it will be helpful for us to address problems that are asked in the assignments and so on. That is why I am doing it this way. I hope it will be helpful. So now that our free body diagrams are complete, let us go about solving it. So let me take this BC first. I know that under the action of these forces, it is in equilibrium. So I will apply sigma Fy equal to 0 because it's having no acceleration. So what does this give me? F pointing upwards minus 30 kilonewton is equal to 0, or F is nothing but 30 kilonewton. So this is one result I have got. So I have solved for F. Now I'll go to the next free body. Let me again apply sigma Fy equal to 0. I have Ra minus 40 kilonewton minus F is equal to 0. But F I have already got it as 30 kilonewton. So Ra, excuse me, I'll just put this page here. Yeah. So Ra is nothing but 40 plus F, or Ra is nothing but 70 kilonewton. It might appear as overkill for some people that why are we going into so much detail when we can simply see that the force applied is this much. It is because if we do these things systematically, when we want to solve the assignment problems, it will be much easier if we make this a habit of drawing the free body and going about. Okay, so now we have got the force. So therefore, force in member AB is nothing but 70 kilonewton, and force in member BC is 30 kilonewton. This we have calculated. Now, what does the question say? That if the average stress must not exceed this, answer the following question. What is the question? It says, what is the smallest allowable value of D1? What is the smallest allowable value of D2? What are D1 and D2? It is nothing but the diameter of these rods. So diameter of AB rod is D1, diameter of DC rod is D2, and the stress is given. So from this, we can actually see that stress in AB is nothing but force in AB by area of AB. We are given that the stress in AB must be less than 140, or rather, let me put it like this. Force in AB by area of AB is equal to stress in AB is what we are given. Now force in AB is 70 kilonewton by area of AB should be less than or equal to 140 MPa. The allowable stress, average allowable stress, should not exceed 140 MPa is what we have. So this means 70 into 10 power 3 to make it Newton by area is pi d1 squared by 4. Area of a circle, so cross section of a cylinder is a circle. Area of a circle is pi d squared by 4, or pi r square, however we want to say it. Should be less than 140 MPa. Now I can simply solve for d1 from here. What does that come out to be? 70 E3 into 4 by pi by 140 squared is coming out to be 25.23 mm. Exactly. So I encourage, as Mr. Ajit has done, I encourage others also to work out these problems alongside as I do it, so that you also are comfortable and enthused enough, so that you don't just see me writing down something. If you also participate, it will be much more interactive and beneficial. And also, since I'm also solving it live, there is a possibility that I might make some calculation errors. So it can easily be caught on time. So D1 comes out to be one thing I have pushed under the rug here. When I take D1 to that side, Actually, I will get the sign like this. Greater than equal to 25. So the minimum allowable is 25.23. 25 is not allowable. 25.5 is allowable. So this is why that constraint minimum was given. So this is coming out to be 25.23. 25.23 mm. Similarly, for D2, we can solve in a similar fashion. This time we can do it a little fast. So for D2, I'll just make a copy of this. BC in BC, stress in BC. So force in BC is 30 kilonewton. So I'll take it to be 30 E3. 30 E3 means 30 into 10 power 3. Because it often happens that sometimes very small doubts might be there, which people might not ask, but it might not be clear. So I just try to put everything out deliberately so that it is clear for everyone, all the people who are attending. So 30 E3 by pi, it was D1 or D2? It was D2. So it will be pi D2 squared by 4 should be less than equal to 140, I think it was, yeah, 140 MPa. Okay. So from here, it is just 30 E3 into 4 by 140 pi root over should be less than equal to D2 if I take it to the other side. So I just solve this. What do I get? 30 E3 into 4 by 140 pi root over this. It comes out to be 16.52. So I encourage you to solve it parallelly and check if my answer is okay. So this has come out to be 16.52. So what have we done in this problem? Let us reflect. We had two cylindrical rods that were to be welded like this, and the forces that were to be applied by some external agency we were given. And we were also given a constraint that the average stress must not exceed 140 MPa in any of the component. So we have to design the component. There are always two parts in this subject. One is analysis. Everything will be given. We have to analyze whether it is safe or not, whether it is within the limits or not. Other thing is the limits will be given. We have to design the components. Design meaning we have to arrive at the dimensions of the components. This is the design part of that. So there is an analysis part, there is a design part. In our questions of the assignments, both these things will be there. There will be some questions on design, there will be some questions on analysis. So it is a good practice when we look at a question, we should automatically assess whether it's an analysis question or a design question. So this was a design question where the constraint was given that the stress must not exceed 140 MPa, and we have to come up with the dimensions. D1 and D2, what are these two? Now another thing one might wonder is the length was given, but it was not used anywhere. What is the use of giving the length then? So here in the question, we were given only one condition, that the maximum stress should not exceed this much. There could also be one additional condition someone might pose, that the total elongation should not be greater than some value. So there the length will also come into picture. So in design also we will have multiple criteria. Presently we have designed it only for the stress criteria. A question might also ask it from the deformation criteria, that the total deformation. Let us say there is some component bed over here, it should not touch that. There is a distance between that. So this is the maximum allowable deflection it can take. It should not go beyond this limit. If we are said, then that also will come into the picture. I hope I have done some justice into explaining this question. If there are any follow-up questions, please feel free to ask. Or could I get some feedback if I'm going in excruciating detail? Do I need to limit going into that much of detail, or it is okay? Could I get some feedback if it is fine, if it works for you? It's fine? Okay, fine.
It
All
is
right.
fine, sir.
Okay, so presently we have dealt with a question that has two components, two cylinders that were welded together. Now let us do the same thing. We will graduate to an actual structure, a truss. And this truss we have number of times we have solved for the forces in our course on engineering mechanics. So let us look at this. A cantilever loading crane used in a research lab is shown in the figure. In If the crane is used to lift a wooden crate of mass 100 kgs, so the mass is 100 kgs, that is given. The truss is made of mild steel. Mild steel has E. E means Young's modulus. Is 200 GPa. And we have already seen in bits and pieces how to convert GPa, what is Young's modulus, what are these components. These things we have seen. So I need not delve much into that. And these are circular rods of diameter 20 mm. So the dia, which is also represented by phi often, is 20 mm. Therefore, area would be just 20 squared pi by 4 mm squared. So this much we know. And then we have the geometry that is given. And we have some questions that we need to solve. So let us go about seeing this. But before we begin, let us see how this is made. So the hinge is not shown actually. If we see at this joint, the hinge would be something like this. So that is not presently shown. Why I am emphasizing on that is one should not think that this member is actually fixed like this. If that member is fixed like that, it becomes a beam. It is no longer a truss. It will also have some bending. But in the question, it is qualified as a truss only. So actually, the hinge will be like this. And then the member is just rectangular. The member is rectangular. The member would have been brought like this and the pin is inserted. So that is clear to understand. So I hope you can appreciate that. Now we have two hinges that are placed at A and B. There is no roller, mind you. Both are hinges. Both are pinned ends. And there is no roller over here. It's a different kind of support we must keep in mind. So now let us replace this. In fact, let me just copy this. One minute. Yeah, I'll just add some pages here. So this is my structure. What we'll do is we will remove the weight and replace it by the mass. The mass that was 100 kg. So I'll just put 100 g. 100 g. I can replace that later always. Or let me just do it right away. What is that? So this is 981. This is my question. That 981 is applied. My first question is asking which truss members carries the maximum tension, maximum load in tension. Okay. looking now, there is one way to go about that. We take a section here, then we take a section like that, we take a section like this, and we take a section like this. We actually exclude all the joints, go by the method of joints, evaluate BD. DD is the maximum tension. Okay, let us see. Good that you are participating. Let us see if that is the case. So it is one way to actually go about the method of joints and arrive at the forces at each and every joint, which is precisely what we will do. But it is also time that we graduate from our engineering mechanics training, and we should be able to quickly at least gauge for most of the members what will be the kind of forces that get applied, that it is induced. So if we just look at this portion, that is, if I were to take this as a structure whole, so this structure as a whole, it gets deformed because of this load. It is held at one end and it is pulled. So from our basic understanding, can we say what will be the nature of force in BC in this member? Tension, exactly. So this will be in tension. If this is getting pulled, this member also gets pulled. So AB also gets pulled. DC compresses. ED also gets compressed. Now, if this is getting compressed, it begs the question, what will be the nature of force here? In this member, as one of them pointed out, that BD will be the answer for this. We will see. Now, from our convention, we know that tension has to be represented like that. Or let me choose another color. It's not bright enough. Yeah, this is better. So, tension has to be indicated like that, as we have seen from our engineering mechanics training. And compression has to be towards the joint. Compression in this member, so the compression would have to be towards the joint. So we have done it for members AB, BC, CD, DE. So far so good. Now if this is the case, we can see that this joint B, under the action of this, will try to move down. But this joint, the member BD has to resist that by the force. So, which is why the member would be subjected to, the member would have to develop a force like that, which means BD is in compression. So BD is not in tension, BD is actually in compression. Now because of the action of this will have to, this joint will try to move away like this. So AD will have to resist it. So it develops tension and resists it. So it will try to pull the joint like that. You try to pull the joint back like that, which is why that is in tension. Of course, this also would have to be like this. Is it clear? This might be a little, this might not be very intuitive, but once we start doing problems, more and more problems on trusses, we can eventually get to a level where we can readily gauge what is the nature. For some members, it might not be very apparent. Mainly for diagonal members, it will not be very apparent to you. But generally, when it is subjected to downward loading, the top would stretch. So top members would be in compression, tension. Bottom members would compress, so those will be in compression. Then based on that logic, you can develop how these members are stressed. Are there any questions? The same thing one can easily do using method of joints. So one can easily take this joint. One can just take a section like this. First, we will take a section like this. At C, we know downward load is 981 Newton.
and then we have a force that is getting applied like this. This is force in member BC. Let us take the force in member CD like this. Then we apply sigma Fx equal to 0, which gives us sigma BC cos 30 is equal to minus FCD. This is one equation. Sigma Fy equal to 0 gives us FBC sin 30 equal to 981 Newton. So FBC is actually 981 by sin 30, which comes out to be, yeah, I have someone answer that. That is good. It is 1962 Newton. So FBC is coming out to be positive, which indicates, it does not indicate whether it is tension or compression. It only indicates that the direction we have taken is correct. So the direction we have taken is correct. So FBC is nothing but FBC we have solved. FCD will be minus FBC 1962 cos 30. FCD is minus 1962 cos 30. It is 1700. That's good. So these two we have. So yeah, for FCD, our answer has come out to be negative. What does that imply? It does not imply tension or compression. It implies that whatever direction we took needs to be reversed. We took FBC in this direction. Answer has come out negative, which tells us that actual FBC direction is this way. Let us see how we have intuitively marked. We have intuitively marked it. 1 minute. FCD. Yeah, when it is marked this way, the force is negative. So we can automatically conjecture. That is what I'm trying to say is, I have taken FCD to be pointing towards the left, which means that actually I have considered the member to be in tension because it is pointed away from the joint. Whereas that is not the case. So the entire thing gets flipped. FCD is in compression, FBC becomes in tension, which is what we see here. So what we have assumed here, this will get reversed like this, and this still remains like this. So if we see these two directions and what we have seen, it is the exact mirror of that. So our signs are consistent is what I'm trying to say. I don't know if I conveyed this properly. I hope it is clear to you. Okay, so we have found out these two member forces. Like that, we can subsequently go about and finding other member forces also, which we will do. But for the time being, let us put our attention on member AE. Can anybody guess what is the kind of force that gets induced in AE, whether it is tension or compression or something else? Compression. Okay.
सर कंप्रेशन होगा उसका.
Okay. See, one thing to note here is, yeah. Any answers? Yeah. Yeah.
Would it
Exactly.
develop any force
So
at all?
the thing is, what is happening to this member? It is connected to two pins, which are connected to, both are connected to hinges like this. There is no roller. There is no movement. So essentially, we have 2 points, and both the points are just remain there. They are not moving. Even if one point moves, that is when the force will get induced in that member. Whereas that is not happening. So this is a zero force member. So the force is 0. Force in AE is 0. I'll just put it like that. Let me use some other color. This is a zero force member. Because of the way how it has been fixed, because of the support conditions. If we had a roller here,
the case would be totally different. In that case, it will get elongated. But that is not happening here because both the supports are fixed. That is why both the supports are fixed in terms of translation, I mean, not fixed from the beam perspective. Both are pin joints. Both are hinged joints, which do not allow any translation, which is why the force in those members are, the force in that member is 0. Is it clear? Someone who had said compression, are you convinced that it is 0? Yeah, yeah. Now,
Yes,
this
sir.
is what we have seen from the support condition. We should also verify whether this is so from the mechanics. So in that case, if we were to isolate this, we have a reaction like this. We have a reaction like this. You can work it out. It will come out to be 0. I don't want to delve too much into that, but I encourage those who have not intuitively understood why this is the force in this member is 0. You can work it out from the method of joints, and I think you will get it. This is equivalent to saying there is no member here. There is a wall or something over here. The wall also doesn't get stretched. AE also doesn't get stretched. So it is just an extension of that. Okay. So which stress members carries the maximum load in tension? We have seen BC. Force in BC has come out to be 1962. Force in BC, this is 1962. Which all are tension. Now again, AB is also a tension member. So from here at this joint, if I just isolate that, I can easily find out what force in AB is. What will force in AB be? Force in AB is nothing but 1962 cos or sine 60. And sine 60 is less than 1. So naturally, our force in AB will be less than force in BC. So definitely out of the tension, this is also a tension member, by the way. Tension member, this is a compression member. So out of the 3 compression members, one is 1962, one we have derived it to be less. So AB or BC is definitely one of the answers. AB is not the answer. CD is a compression member. DE is also a compression member. AE we saw is 0. BD, B and D is also a compression member. AD we have to see. How much is the force in AD? We will have to see. This we can calculate. Now at this joint, if we take a section like this, using the method of sections, we are well aware how to solve for this. So I won't delve much into that. I encourage the participants to solve this and try to find out if AD also will be the answer. When I will be posting this sheet, I will post it with the complete answers because there has to be some engagement on the participant level also, which is why I am leaving some things untold so that you can work on it on your end. Now that this is done, let us go to the next question. What does the next question say? Which truss member carries the maximum load in compression? We saw this is in tension. In compression, which is the one? Will it be DC or will it be ED? This is something we have to see. Okay, so let us isolate this joint. Now we know at joint D, we know the force here is compressive. So this is towards this, and here also it is compressive. So this is force in A, B, C, D, E. So this is force in CD. This is the force in ED. Force in AD.
Now we know what this is. This is equal to 1700. And FBD we can solve from here. If we take this, FBD is nothing but FBC cos 30. I'm not going too much into how this is solved because this is what we have been doing through the entire course of engineering mechanics. If the same thing we are also doing here, it won't be any value addition. So I leave this to the audience to do it, but I'm just giving the broad strokes here on how to solve this. All right. So FBC, we know FBC came out to be 1962. So FBD is nothing but 1962 cos 30, which also comes out to be 1700. I'm sorry, it will be cos 60 actually, because this angle is 60. So it will be cos 60, not cos 30. So FBD is nothing but 1962 cos 60, which is half essentially 981 Newton. Okay. And broadly speaking, if I take just this section, if I just take this section of the truss, I know that whatever load I have applied downward has to be balanced by my inclined member only, because other two are horizontal. There is something that has to provide the vertical equilibrium balance, and I can simply calculate it based on that. So FAD sin 30 will be nothing but my W, that is 100G or 981, or FAD is nothing but 2 into 981, which is 1962. So FAD also comes out to be 1962, which is same as FBC. That is why both are correct. I hope it is clear to you what we are doing. So this has come out to be 1962, and this is actually tension. So this is correct. In which case FED, we can calculate it from here. FED minus 1962 cos 30 minus 1700 equal to 0. FED is nothing but 1962 cos 30 plus 1700 comes out to be 3400, as someone has correctly solved it. So since I'm also solving it in real time, there is a possibility there might be some calculation errors. My focus is not so much on the values, so to speak, although that is the final goal. My approach is more towards my focus is more towards the approach to the problem. I hope you can appreciate that. So FED is 3400, which is in compression. So we know from here that the maximum compression is being taken by F member ED or DE, whatever that is. Then we have the question, the maximum tensile stress is carried by member so and so with so much of stress. Now it is just a cakewalk. Now that we have got all the stresses and nature of stress in all the members, it is just a matter of invoking our understanding of stresses and strains. We know stresses, for now, stress is nothing but P by A. P we have got, A is given, the member dimension is given. So we can simply calculate A. We just need to calculate the stress in each member. So if we have calculated the maximum tension to be 1962, the maximum stress, the maximum tensile stress is nothing but tensile is nothing but 1962 by what was the area? Area was 20. Diameter was 20. So area is 20 squared pi by 4. So what does this come out to be? 6.24. Is there an answer like that? 6.24 BC. Yes, very well. 6.24 BC. Similarly, we have been asked for the maximum compression. Maximum compression we found out to be 3400. So it is 3400 by 20 squared pi by 4, which comes out to be 10.82. Is there any answer like that? 10.82 DE. Is member DE our correct DE? We found out that this member ED was undergoing the maximum compression, which was 3400 Newton, which someone had also calculated. So just that 3400 by 10.81 gives us the maximum stress. So far we have dealt with only stress. Now we are being also asked what is the magnitude of maximum deformation in the truss member carrying the maximum tensile load. So how can we do this? We have a recipe for this, which we discussed earlier here. So what is the maximum deformation? The deformation is nothing but PL by AE. Do we know the length of the member? We know. Do we know the force that the member is carrying? Yes. We know the area. We have been given E. So let us just calculate it for one member. For the other member, I leave it to the audience to do it. So for the member carrying the maximum tensile load, P is 1962 Newton. Area is 20 squared pi by 4. E is, what is E? 200 GPa. 200 GPa. So E is 200 GPa. And L. Now let us look at it from the question. What is L? Is L given? We know that these were the members that were carrying the maximum tension. And from the very arrangement, we can see both are of the same length. If they were of different length, then we need to calculate the force, the change in dimensions in each, and then report the maximum one. Presently, they are both of the same length. So the length is nothing but, this is 4. And from here, we can easily see that it is what? 4 by sine 30. So it is 8, essentially. So 4 by cos 30. 4 by cos 30. So it is 4.61 meters. I hope so. The length cos 30 is length of DC by length of BC. So length of BC comes out to be 4.62 meters. So we have the length also in the member, and this is in meters, mind you. Copy. Let me go there. Yeah, so the length of the member is this much. Now it is just a matter of calculating what is the maximum deformation. Maximum deformation is P62. But why don't I do it here? It is 1962 PL by AE, right? So delta L is nothing but PL by AE. P is 1962 into 4.62 meters. So I converted that to mm, divided by area is 20 squared pi by 4 into E. E is given in 200 GPa. Presently we are doing everything in Newton per mm square, which is MPa. So 200 into 10 power 3 we have to do. So these conversions, one should keep it in mind and be comfortable with them, so that one is able to do it quickly. Into 1962, I think. 1962 into 4.62 E3. So this comes out to be 0.144 mm. I encourage the viewers to solve this once and see for yourselves whether it is correct. Now the answer is asked to report in 10 power minus 1. So what should we do to our answer? We should multiply it by, we should divide it by that value. That is delta L is actually 0.144 mm. If the calculation is correct, let me just check it once. Into 1962 into 4.62 E3. Yeah, 0.144 exactly. So 0.144 mm is my answer. However, I have been asked to report it in. I encourage all those who are taking the assignments, you please finally read the question again as to how it is asked, in which format, so that you don't lose out. So it is asked in 10 power minus 1. So essentially I have to divide my answer by 10 power minus 1 and then report it. 0.144 by 10 power minus 1, which is nothing but 1.44 into 10 power minus 1 mm. So I should report my answer as 1.44. And since magnitude is asked, I have to report the absolute value. It did not matter in question 16 because it was tensile stress. In question 17, it will be compressive stress, but still I have to report the magnitude. I hope that is clear, and I will leave question 17 as an exercise for the viewers to do it. Anyway, so we have run out of time. So I hope I have done some justice in explaining and giving an overall introduction to the course as for the first week. So I hope it was helpful for you. So if there are any questions, you are welcome to ask them. Was it clear? Is my speed okay? Is my delivery fine? Or is there any feedback on that or the content I have covered? Yes, please go ahead. बताइए. Yes, Mr. Rajkumar.
यस
ये
सर, ये जो
पीडीएफ,
आपने
हाँ,
जो
ये
सॉल्यूशन
पीडीएफ
किए हैं
भी
वो
आपको
मेरे
जैसे
पीडीएफ कहाँ से मिलेगा?
स्वयं
तो
का जो
मेरे को
पेज
चाहिए।
है वहां पे लेफ्ट साइड में नीचे लाइव सेशन लिखा हुआ आएगा. आप उस पर क्लिक करेंगे तो वो आपको एक एक्सेल फाइल पे ले जाएगा. उस फाइल में ये जो जहाँ पे मैंने अभी सॉल्व किया है इसका पीडीएफ भी मैं अपलोड कर दूंगा, और ये जो आज हमने किया है इसका रिकॉर्डिंग का भी लिंक वहीं पे आपको मिल जाएगा. रिकॉर्डिंग मैं आज रात तक मैं अपलोड कर दूंगा और ये शीट भी मैं आज रात तक. I'll try to upload the sheets and the videos preferably on the same day as far as I can. So if it goes beyond one day, I request you to please bear with it. But more or less it will be available within that day. और उसका लिंक आपको वहीं पे स्वयं पेज पे ही मिल जाएगा, है ना. और नहीं तो ये जो वीडियो मैं अपलोड करूंगा दिस विल बी अ यूट्यूब वीडियो
थैंक
विच
यू
आई
सर।
विल अपलोड. आई विल ऑल्सो गिव द लिंक ऑन द इन द डिस्क्रिप्शन इफ नीड. ऑलराइट. So all right then. Any other questions? Anything else?
सर क्या ये लेक्चर रेगुलर चलेगा क्या, या वो सिर्फ वीक में एक?
हाँ, वीक में एक चलेगा. हर हफ्ता एक होगा एंड इट विल कवर द कंटेंट्स ऑफ दैट वीक. नेक्स्ट वीक फ्राइडे को हम वीक 2 के कंटेंट्स देखेंगे.
ओके सर।
ओके, या, ऑलराइट. Any other questions? Anything, any feedback? Anything you want me to cover specially? Okay, all right. And I hope my delivery is okay. So if there is anything you find that is deficient, if I'm going too fast, if I'm not articulate enough, if you want me to explain in some other language, session was very helpful for gate journey. Okay, I wish you all the best with your gate journey as well. Good if it was helpful. I'm very happy. And do try to attend the sessions in the future also. It'll be the same Google Meet link. We'll be meeting every week so that we can try to address this. And just one more thing I want to add. In the assignment, there will be one question on bolts and sleeves. I don't know if anybody has looked at the assignment yet. The idea is that these sessions should also help you to
address the problems in the assignments. So for the most part, everything is covered. For the bolt and sleeve question, I'll just give you a brief of what it entails so that you can make an attempt. I will not be solving the question fully because the dictum is we are not supposed to solve the assignments that are live. But I'll just give you a flavor of what it entails. For interested people who are staying back, I'll just take 2 minutes. I'll just explain. Ji, namaste, sir. Okay. Yeah, so I'll just explain what it entails so that you know people who are interested can make an attempt. Basically, it has a sleeve. We have a sleeve and then we have a bolt like this. There is a misfit. The length is a little bit more. And we have another end to this where there is a thread and we are trying to tighten this into place. So we have to tighten this into place in order to make both the lengths same. So what is the stress and strains developed in both these members is what is asked. So in the question, in the lecture also, there is one a bolt and nut problem that is discussed. This question is very similar to that. What it is saying is, in order for me, presently it is here, when presently it is like this, that is, this is distinct, my lengths are like this. So in my final configuration, this would have come here, this would also have come here, and my cap would have gone there. So now you can figure out if this is the sleeve. And let us say this is the bolt. Now from these two figures, the left side matches, okay? The left side matches. What happens to the right side? This is the final position. This is my final position. This is my initial position. And let this be the cap. Let this be the thing that we are trying to tighten. So I will just put it here. I'm just keeping it here. I have not tightened it, mind you. I'll just put it at a little bit of distance so that it is clear. So with this background, what can we say about what happens to the sleeve? What can we say about what happens to the bolt? And how much has this thing moved? So this is something you need to find out in order to solve this issue, solve the problem. So I encourage you to ponder over this. Anyway, this PDF will be available. Yeah, sleeve reduces. Okay, the pink one is the sleeve. So is the sleeve reducing or elongating? Elongating. And is the bolt getting compressed or it is getting pulled? So with that, I would encourage you to approach the problem and give it an earnest attempt. So anyway, I suppose you will get the rest. So similarly, there will be two unknowns. So there are two equations. What are those two equations? One comes from our compatibility of displacements. One comes from our equilibrium, sigma fx equal to 0. With that, you should be able to solve. Other than that, I have nothing more to say today. So if there are no questions, we can call it a day. Excuse me for overshooting the time by 10 minutes. I'll try to keep it within 2 hours starting from the next session, which will be coming Friday, same time, 6 to 8, and same link throughout the duration of this course.
There is one more
So if there
problem
are
in the
any questions,
assignment.
yes, sir.
There is one more problem in the assignment which deals with the steel rod and copper rods.
Okay.
and how to tackle it?
Okay,
It is just
so
directly ask
let
what
me
is the
also,
stress in that.
yeah. So basically, I'll just give another approach to go about doing it. So I have a mass, and then I have a I have two steel two whatever those are, whichever material that is, and then I have a longer rod, something to that effect. Now my idea is this has a mass or a weight or whatever that is. We know what is the allowable sigma. We know what is sigma allowable in both of them. So there will be one equation that comes from our force equilibrium. Let us say I separate all these out. I will have forces like this. This will be the force in the middle one. This will be the force in the extreme ones. Correct? So it's the same thing from Newton's third law. We know it will get applied like this. So we have one equation with equilibrium equation. The other one comes from displacement compatibility. Now for displacement compatibility, if this mass, let me go back to the original this thing. If this mass goes down by one amount, what is the compression that, let us say that this mass has gone till this point. Can we see that the compression, the distance, the change in length in both the rods, are they equal or are they unequal? This bar, this weight is rigid. So under the weight, let us say that this weight has moved here because of the deformation in the rods. Now you can just assess whether the deformation in the middle rod is more or the end rods are more. Change in length is equal. So with that, you can approach the problem and try to address it.
Okay.
All right. Yeah. Okay. Thank you. All right then. So perhaps we'll, thank you. So if there are no further questions, we can call it a day. We'll meet next Friday. I welcome all of you to attend. Thank you.
Thank you.
Thank you,
Thank
sir.
Yeah. Thank you. Thank you. Okay. So I'll end the meet.